So chemical formulas, as we start moving forward, you are going to have to be able to read chemistry when it's written like this. So you'll need to be able to break down a chemical formula and see what atoms are present and be able to figure out some things about it depending on what kind of bonds you're looking at in these chemicals. So chemical formula is the term we use for any written way to describe a chemical, be it covalent, metallic, or ionic. It doesn't matter which one it is, we're still going to call them all chemicals. But we're going to get into some specific differences between ionic and covalent that the guy in the video didn't cover for you. So first, the basics, which you should have seen. Any subtext numbers that look like this, they're down at the bottom, are going to apply to the element that's before it. So H2O, we have 2 hydrogens. And we have, there's an invisible one here, 1 oxygen. We don't write it like this, but if you need to think about it when we start getting to the math, just like you would say 1x, we'd write it as x, there's an invisible one there. All right, so here we have 2 hydrogens in atoms and 2 oxygen atoms. This is where it's going to start looking a little bit more complicated. What we have here is a magnesium atom and 2 of these groups. So this nitrogen with 3 oxygens, I have 2 of these. On the video that I posted earlier, the teacher wrote it out like this. So if you're a visual learner, this is how you could visually represent it to see that there are 1 magnesium, 2 nitrogens, and 6 oxygens. If you like written math and written math is more comfortable for you, there's another way that you can write it. So I can also distribute this to, right? Distribute it to this 3 and distribute it to the invisible one that's right here. So then I could write it out like this, where I have magnesium, nitrogen 2, oxygen 6. That tells me right away I have 1 magnesium atom, 2 nitrogen atoms, and 6 oxygen atoms in this. We don't write it like this though. So you can write it like that if you're thinking about it and needing to work through something visually, but NO3 is an ion. So we will always find it together, which is why we write it like this, because it's its own like singular unit piece. So that's our first rule, is our subtext is going to apply to whatever comes before it. If it's on the outside of parentheses, it applies to everything in the parentheses. The next basic rule is that numbers in front of a molecule apply to all of the atoms. If I say 2 H2O, it just means I have 2 molecules of H2O, right? So then I would distribute the 2. I would have 4 hydrogen atoms and 2 oxygen atoms. I will fix that before I post this. So, and if you picture it, you can see it. I have 2 oxygen atoms and 4 hydrogens. When I'm dealing with the more complicated ones, right, I can imagine like there's big brackets here. And then I'll do whatever's on the inside first. So I would distribute my 2 out, figure out how many magnesiums, nitrogens, and oxygens I have in my original molecule or my original chemical, and then I would distribute out the 2 at the beginning. This one in particular would tell me that in 2 magnesium nitrate that there are 2 magnesiums, there are 4 nitrogens, and there are 12 oxygens. Right, so those are our 2 rules for figuring out how many of each element we have. Once we follow those, then we just have to look up what the symbols are. We do have 2 different names. So molecular formulas are specifically for things that are covalent. Let's not move that. Things that are covalent are going to have molecular formulas because they are molecules. So our molecular formula is going to represent a single molecule of a covalent compound. If I presented you with a picture like this, you could figure out its molecular formula by counting the atoms. Usually we're going to list them in this order. Carbon comes first, then hydrogen, because carbon and hydrogen are super common in our Earth, right? We're carbon-based life forms. Carbon is the basis of all biology. and then any other elements that are present are in alphabetical order. There are some things that are not going to follow this. Acids and bases have some special rules, right? But if I gave you a picture of something and you followed these rules, even if it's technically not how we wrote something, it would be fine. And any chemist, as long as you had your numbers right, could figure out what the chemical was. Okay. Usually we're going to use specific colors to represent things. So in this diagram, our carbon is black. Carbon is usually black. Hydrogens are usually white or gray, and oxygens are usually red. If I give you a picture like this, I will give you a key. I don't expect you guys to remember that. If you study biology or chemistry in college, though, those will start to feel like second nature. So I already put these in order for us: carbon, hydrogens, and oxygens. So we can see that there are 6 carbon atoms in this molecule. We put the 6 down. There are 12 hydrogens if I go through and count them all. That goes next to my hydrogen. And there are 6 oxygens. If you remember from biology, this is a really important molecule. It's glucose. It's sugar. Okay. So this is what it actually looks like with all of the atoms together. These are the bonds. It's covalent, so this is where they're sharing those electrons, are these bonds that are shown here. Okay, ionic formulas are a little different. Ionic formulas represent a ratio of the ions present in the ionic compound. If you have a grain of salt, of table salt, that's basically one big molecule of salt. They're all connected. They're all bonded to each other. Because we have a negative chlorine ion, it wants to be next to the positive sodium ion, wants to be next to the negative chlorine ion, wants to be next to the positive sodium ion, right? So they create these lattice network, so like an organized grid where they're all next to the other ions. So I don't want to say that there are 100 sodiums and 100 chlorines in this piece of salt. That's not helpful information. So when we're talking about ions, we only talk about the ratios. So for sodium chloride, I have 1 and 1 in the ratio of how they line up. So it would just be sodium chloride. If here, like iron oxide, I have 2 irons and 3 oxygens, so it's a 2 to 3 ratio. If I had a piece of this, right, just like this, they're all connected, it's basically one big molecule, but we just list the ratio. Here, where we have more atoms than you would expect, this sulfate is actually one big ion. It's an ion made out of multiple atoms, so we call it poly or many atomic ion, an ion made out of many atoms. And we have a 1-to-1 ratio between these ions, right? Because there's one of these. Okay, some quick information about ionic formulas. The first half of an ionic formula is the cation. This is the positive ion. The second part is the anion. This is the negative one. If you're visual and want a way to help you remember that, I always remember it cat ion with a big positive in the middle, and an ion with the big negative across the A, but there are different ways that you can remember it on your own. Our cations come first, our anions come second, positives before negatives, good things before bad things, right? It's just the order that we write them in. If I gave you 2 ions, you should be able to figure out the ratio that they would need in order to get to a net charge of 0, which is what they're aiming for. So if I told you you had iron 3 ions and oxide, I'm going to draw this out real quick. My first iron ion would have 3 positive charges. If I added in an oxygen ion, it would only have 2 negatives. So I would need another oxygen ion called oxide. I'm still not even, so I could add another iron ion right, that has 3 positive charges, and then I could add another oxygen ion with 2 negatives. These now have equal charges, 6 positives and 6 negatives. So this is the ratio that we're going to see, which means that this would be Fe2O3 because it took 3 oxygen, 3 oxides, and 2 iron ions to become even, right? This is the long way to get there. There is a shortcut, which is really easy. Whatever my charge is on the first one, on my cation, I'm going to go put it as my subscript on my anion, and whatever my charge is on my anion, I'm going to put as my subscript on my cation. It'd be Fe2O3. I'm going to check my charges real quick. I put them in brackets just so I can see there's 2 of this with 3 charges and 3 of this with 2 negative charges. Altogether here, I have 6 positives and 6 negatives. Those are equal, so I know that my ratio is correct. But that is it for the information I have for you guys on types of bonds and how we read chemical formulas. Does